This lesson is on 2.8. It's part 1. We're going to split it in half. And today we're going to focus on compound inequalities and solving absolute value equations. So two different ideas here. And we're going to start out with compound statements or compound inequalities. And they're made up of one or more equations or inequalities. If you have these, we are talking about the first ones being disjunctions. All right, and a disjunction is a compound statement that uses the word or as, uses the word or and is true if and only if at least one of the parts is true. So with the word or, I like to remind you that it could be one, the other, or both parts that make it true. And then the other thing to remember, if it's not a special case, we are looking for a split. Normally with or, we get our answers on the number line to go two different directions. Now, there are special cases where it might be all reals, but normally we have a split where they go two different directions. All right, so we have an example here. X is less or equal to -3. I needed to add that negative there to make this work, or X is greater than 2. So in set builder notation, it's simply the brace X such that X is less or equal to -3. They replace the word or with the union symbol, which means or, X is greater than 2. And that's it. I also want to talk about interval notation, but I thought maybe graphing this might help us. So let's do a quick sketch. Here we are at -3. Always an even interval on your number line. Show a couple numbers, maybe above or below. So let's go ahead and graph this. X is less than or equal to -3 would be a closed circle. Now I normally like to show my test graph above, and then X is greater than 2 would be here. So it looks like your typical split. So go ahead and I'll drop that. I do have a reason for showing the graph above, because this is not always my final graph. So by doing a little test graph above, I can see what's really happening. So this is what it looks like. My answer is either down here below -3, or it's up here above 2. So those are my two options, one or the other, and there is no overlap. Now, for interval notation, I want to remind you that it goes from low to high, and we have two separate intervals. We have this group down here, which would be from -infinity up to the high of -3, which is included, union symbol, and we jump up to 2, which is not included, to positive infinity. So that's what our interval notation looks like, two separate ideas for each piece. All right, if it's not an or statement, the other option is an and statement, which is a conjunction. So a conjunction is a compound statement that uses the word and is true if and only if all of its parts are true. So in this one, we're looking for overlap. All right, we're looking for where do these two overlap. Doesn't always happen that way. There are special cases, but a lot of times you'll see the two graphs doing this, and what you're looking for is where do these graphs overlap. And so I would collapse these graphs, and this would be my answer between here. All right, so we have these same numbers, but notice the signs are flipped. And in here, when they go to do set builder, X such that X is greater than or equal to -3, and that is your intersection symbol, X is less than 2. So let's go ahead and talk about this on a graph. And so here we are again at -3. All right, X is greater than or equal to -3 would start here with a closed circle, and we would shade going this way. X is less than 2 would be an open circle, and shade going that way. And so when you go to look at this, the and statement is where they overlap. And this is where they overlap, from here to here. So I'd have a closed circle because it's included on X is greater than or equal to -3 and as X is less than 2. But this one would be an open circle because it's not included on both, and then we would only shade what's in between. Okay, so that is what my final graph looks like. Probably could have done a little better job on that. So that's what it looks like. So interval notation, we don't have two separate ideas here, we have one. And the low is -3 and the high is +2. The low -3 was included and the 2 was not. So bracket here, parenthesis here. So that's how you can write it with the word and. You could also write it in set builder, but there's also a single statement, and it's important to understand this is the same thing. X is greater than or equal to -3. X is less than 2. And so you'd read this, -3 is less than or equal to X, and X is less than 2. And if you can look, it comes right here. So here's the low, here's the high, included, not included. So whether you see the word and or as a single statement, this also represents an and statement. Or statements will always have to have the word or in it. Okay, so I just took about 5 minutes or so just to introduce this idea, so let's go ahead and get moving. We're going to solve each compound inequality, and then we're going to graph the solution set, and I'm going to add on to here interval notation because we want to keep practicing that. So we're going to add in our interval notation. So when I look at this, I'm solving two separate inequalities. So I'm going to subtract my 3. I have x is less or equal to 2. Keep the word or there, I don't want to lose it. Divide both sides by 3, two separate ideas. X is greater than 3. So it's an or statement. There should be a split. There may or may not be. So here's 1, here's 2, here's 3. We'll add a 4 in there. And x is less than or equal to 2 would be a closed circle, and we would shade that way. X is greater than 3 would be an open circle and shade greater. So it looks like your typical or statement. I'm going to go ahead and finalize that. When I grade, the only thing that I'm grading is what is on the graph. So if you leave that answer above it, I'm just going to assume that's your test run, and I'm looking for it to be on your number line. And again, some of you might think, well, that's pointless. You just did the same thing. This is going to save me from making mistakes later when we have special cases. So that is your typical or statement. That is my graph. And then if I was doing an interval notation, the graph helps me. I see that it goes from -infinity up to and including 2, union for the or, and it jumps to 3, which is not included, and it goes to infinity. And that is my interval notation. If I want to put this in set builder, I can just put the brace on it, x such that, and then fill this in with my brace. Okay, over here I have an and statement. I'm looking for overlap. So first, when I multiply or divide by a negative, are you going to remember to flip your inequality symbol? Keep the word and, we certainly don't want to lose that. And then add 3, and I get x is less than or equal to 5. So there are my two answers. Let's go ahead. I need some numbers here. Here's -5, 0, and +5. All right, so I have all my numbers in there. X is greater than -4 would be an open circle, and it would shade this way. X is less than or equal to 5 would be a closed circle, and it would shade this way. So with that in mind, I do have an overlap. It's an and statement, so my overlap, it starts with an open circle, because the -4 is not included, and it goes to a closed circle. And again, we go ahead and we shade between. So imagine collapsing these and pulling the overlap from it, and you're getting rid of everything above and everything below it. So your answer could be written a couple ways. You could write it with the word and, or you could write it as -4 is less than x. So I'm rereading it. -4 is less than x, which is less than or equal to 5. So here it is with the word and. Here it is as a single inequality, that compound inequality. Interval notation, the low is -4, the high is 5, and that is included. So you can see the similarity here, but we pull the x and we pull the inequality. All right, we have two more inequalities before we change, so go ahead and pause now, and it would be a great time for you to go ahead and try these. All right, I'm hoping you paused and you gave these a try, but it might have looked a little different. I'm getting here x is greater than 4. Keep my or, I don't want to lose that. That has to be part of my answer. And I'm divide both here by 3, and I get x is greater than or equal to 6. And if you're really looking at it, you can see that they're both greater than, where my other statements seem to have different inequalities. So that should tip you off that something is different here. So we'll go ahead and we'll start. We'll count by 0, 2, 4, 6, 8. It's a little bit off there. Okay, I have an open circle at 4, and it's shading going greater than. And I have a closed circle at 6, and it's shaded also going greater than. And that's different, okay? If we weren't paying attention, you might make it go down below 4 and greater than 6, but they're both greater than. I double checked to make sure I didn't miss anything. All my signs are correct. This is a special case. It's an OR statement where they both run the same direction. So an OR statement is one, the other, or both. So here, one is true. Here, they're both true, which means any of these answers would work. If I pick a number like 5, 5 is greater than 4, but it's not greater than 6. So that's okay as long as it works in one or the other. If I pick a number like 8, it works in both, and that's okay. So if it's an OR statement, we get more answers. I start with my open circle at 4, I include this part, and then everything else above it. So it almost gets rid of the x is greater than or equal to 6, because that is enveloped by the lower answer. So with an OR statement, you would not put a circle on 6 because it's already included with x is greater than 4. So this would not be your final answer. Your final answer is just x is greater than 4. That would be your final inequality. As interval notation, it would be a parenthesis 4 to infinity. So that 6 is not being included anymore as part of an answer that stands out because it's just part of the answer overall. So be really careful with that. Now, if this was an AND statement, just want to show you this real quick. If this was an AND statement, then, and I had that at 4, and I had this at 6, here's 4, here's 6, and this was an AND statement, and means they have to overlap. So my answer would start at 6 and then go forever. And so all of that would be thrown out because they're not both true here. And so my answer would be x is greater than or equal to 6 or 6 to infinity. So be really careful. This is a special case for OR where you have more included. And in AND it's a special case because we have overlap but they're in the same direction that goes to infinity. So I just want to throw that idea out there. Okay, so when we go to do this one, I hope this didn't throw you off. It's 1/2 times C. So you could divide by a half. I prefer to multiply by the reciprocal. And so I get C, keep my less than or equal to sign. C is less than or equal to -4. The word and is key here. And then we're going to have to do 2 steps here. So 2C is greater than 0. And that's okay. Divide by 2. And I get C is greater than 0. So those are my answers. Now it's an AND statement, so I'll have a lot of people will come down here. I will go -6, -4, -3, -2, -1, 0. Okay, so I counted by 2s, but I showed every 2, but I counted by 1s on my chart. A lot of people just come in and they'll put a circle and they'll go from -4 to 0 and call it a day. But if you look at this, x is less than or equal to -4 and C is greater than 0. So these are the reasons why I do my little test graph above to see what happens. My number line should stay blank. I have no solutions. Okay? Since my number line went below and it went above and the word here was and, there is no overlap. So there are no solutions or the empty set, and your graph should be blank. There shouldn't be any shading on that graph to get full credit. Okay, it's really important to get your compound inequalities done because the second half of the lesson that we're going to do after this next piece is going to be absolute value inequalities, and they are going to come right down to what we just did here with ands and ors, with disjunctions and conjunctions. For now, we're going to flip it on over and we are going to talk about absolute value. Now, this is all an Algebra 1 concept, but it is something that we need to revisit. So recall that the absolute value of a number x is written the absolute value of x, these straight up and down bars. It's the distance from x to 0 on a number line. So 5 is 5 units to the right of 0, and negative 5 is 5 units to the left of 0. It doesn't matter whether it's left or right, they're 5 units away. You have to move 5 units away. The positive is positive to the right, negatives to the left. So absolute values will always come out to a positive answer because we're talking about distance. Now, if I change something on the outside, that changes everything. So same idea, the absolute value of x. If I say, hey, the absolute value of x equals 3, what could 3 be? Sorry, what could x be? X could be 3 or negative 3. So if I said I have the absolute value of x equals 3, well, x could be a 3 or x could be a negative 3, because the absolute value of 3 is 3 and the absolute value of negative 3 is also 3. So absolute value will always have two outcomes. Now we are focusing on the absolute value equations today. We are going to focus on absolute value inequalities tomorrow. And they're talking about the absolute value is less than 3. Less than is an and statement, and greater is an or statement. So I like to use the idea of less and instead of less than, and great or instead of greater. So less and great or. And we will talk about that more as we move through the lesson. But again, today we're going to focus on equations. So let's go ahead and look here. For all real numbers, we have the absolute value of x is a. What's inside could be the positive version of a or the negative version. All right, so we have to look at both things. So let's make this a little bit easier to see. Again, these rules apply to inequalities just the same as what we're doing here. So we're focusing on equations today. So the first thing I'm going to do is I'm going to separate this. You don't have to do it this way, but I think it helps. What we're saying is I have the absolute value of something that gives me 5. The absolute value of 5 is 5, and the absolute value of negative 5 is 5. So I like to look at it as what's inside. X minus 7 could be negative 5, or x minus 7 could be a positive 5. So I'm not saying what x is, I'm saying what's inside could be a positive or a negative 5. And so we solve. We would just solve our equations very simply. X is 2, or add 7, x is 12. So those are the two values of x. Now if we take that and we plug it in to check it, just to show you how this works. For this one, these are my answers. I'm just going to circle them. I have two outcomes. I would plug in the 2. So it'd be the absolute value of 2 minus 7, which is the absolute value of negative 5. And yes, it's true. It works. Come in here with your 12. The absolute value of 12 minus 7. Well, 12 minus 7 is 5, and the absolute value of 5 is 5. So both of those answers work. When you do absolute value, treat this like it's in parentheses. You do what's inside first, and then you take the absolute value of one number. Now, one of the things you have to do is you have to isolate the absolute value. So I'm going to write that rule in here. The first thing you have to do is isolate absolute value, almost like you're solving for it. And then you can break into it. So this one started out with the absolute value being on the left by itself. This one has a positive 5 here. I want to focus on this, so I want to move the 5 over. So I have the absolute value of 3x is equal to 9. Now I can start my problem. What's inside 3x could be a negative 9, or what's inside 3x could be a positive 9. So whenever you're looking at this, again, I'm not saying what x can be, I'm saying what's inside. I could have a negative 9 in here or a positive 9 to get me the 9. So we're making 3x be negative 9. That would give us x is negative 3. Or divide both sides by 3, x is positive 3. So these are my two answers. And again, to check it, we go back to the original. I'm going to check it over here. 3 times negative 3 plus 5 should be 14. Okay, well that's the absolute value of negative 9 plus 5 is 14. Well, the absolute value of 9 is 9. 9 plus 5 is 14, so it works. If we check the 3, that works. 3 times positive 3 plus 5. So that would be the absolute value of 9 plus 5, and the absolute value of 9 is 9, so we get 14 equals 14. So we always can go back and check. So absolute value, you want to remember to isolate the absolute value and then to break into 2 answers. Break into 2, I guess we'll say 2 equations or 2 inequalities when we get there. So let's go ahead and look at these last 2. First thing I want to do is isolate the absolute value. Nothing in, nothing out. I talk about little absolute values being little armored cars. Nothing can go into this, nothing can go out. So what's in here will always be in here until we break it out by accounting for it. So first we're going to get rid of any addition and subtraction. And I have 2 times the quantity negative 3 plus k is equal to negative 4. Okay, then I'm going to come and isolate by dividing that 2 out. And I have the absolute value of negative 3 plus k is equal to negative 2. And I can tell you right now that there are no solutions. I'm done. This is the absolute value. Can the absolute value ever give me a negative outcome? No. Not unless there was something outside and we isolated it, so there's no solution. So you really want to look for that. The absolute value cannot be equal to negative. Now let's say you weren't really seeing that and you just started going. And you would have said, hey, what's inside negative 3 plus k equals a negative 2, or what's inside equals a positive 2, which would actually keep the negative sign. So negative, positive would be the same negative sign there. So then I go to solve it and I get k equals 5, or I subtract 3, I add 3, and I get k equals 1. If I take this 5 and I plug it in, 2 times negative 3 plus 5 plus 14 should equal 10. Okay, that's 2 times the absolute value of 2 plus 14 equals 10. That's 2 times 2 plus 14. Well, that's not going to work. That's 4 plus 14. That does not equal 10. So you can see that I get a false answer. Same thing if I tried putting 1 in there. 2 times the absolute value of negative 3 plus 1, I'm going to get the same outcome. I get 2 times negative 2 plus 14. Well, that's 2 times 2. And again, I get that same outcome that does not equal 10. So I would know that I got it wrong if I check it, even if I missed this. Now, if this was a negative 10 to start with, I cannot just assume there's no solution, because I might have canceled it out by moving something. So here's a good example. When I go to look at this, and this is our last one, when I go to look at this, if you say, oh look, absolute value is equal to negative, you can't judge it that quickly. It has to be isolated for you to determine anything. It has to be isolated before you can break it out of the absolute value sign. So start by adding 6, and that turns everything around. So I have 2 times the absolute value of x over 4 is equal to 4. Then I'm going to go ahead and divide out the 2, and I have the absolute value of x over 4 is equal to 2. And that's fine. That we can do. Make sure this looks like an absolute value there. So now that I've got the absolute value isolated, I could take the absolute value of 2 or negative 2. So what's inside x over 4 could equal 2, or what's inside x over 4 could equal a negative 2. And then since it's divided by 4, I'll multiply out, and I get x could equal 8 or negative 8. X could equal negative 8. And then you would go back and you would take your answers, take them and plug them in, and see that it works and gives you negative 2. Okay, so I'm going to repeat this again. Absolute value is really important to isolate it, and then you don't change what's inside. What's inside never gets changed. So once you isolate it by getting rid of a number outside or getting rid of the addition and then the multiplication, then you can focus on breaking it up. Absolute value can never be negative, so that would always be false. That cannot be true. absolute value cannot equal a -2. Or here, once we isolate it, again, we break it up and say I could take the absolute value of a 2 or a -2 to get that out. All right, last reminder on the front, your compound inequalities. Ors typically look like a split. Check out that interval notation. But sometimes ors are special cases, so one, the other, or both. Ands are normally overlap. Interval notation looks like this. But sometimes we have a special case where they don't overlap. And so how do I know it's a special case? Because an and statement graphs like an or statement. And that means there's no solution. Or an or statement almost looks like an overlap of an and statement. So there's one more thing that could happen that I'm going to show you. And that one more thing that could happen is if I had an and statement, if I had an or statement that went like this. Let's say this was an or statement and I went to graph it. If I wasn't paying attention, I would think, oh, well, it's everything. 1, 2, 3, 4, 5. You might think, well, everything, or if it's an and statement, you might only go from here to here. But if this was an or statement, then this would be all real solutions from -infinity to infinity. Because in this one, anything down here works, anything up here works, or anything in between. So one's down here, the other's true's up here, or together they're both true. So I just want to throw those reminders. If an or statement looks like an and's overlap, it's actually infinite solutions. So check out those special cases as they come up.